Hello everyone, this lesson is going to be on pulleys and it covers section 10.6 in the book, and I'll be going over a simple example on pulleys and then you can do some problems yourself. Okay, so here's section 10.6 on page 173, refers to pulleys. I'm going to go through example 13 on the simple pulley. Now, if you are not sure what a pulley is, we can go to Google. These are some images of pulleys, and this is what they're used for. Basically, what they're used for is to, well, you can make a machine. That is, by what we're doing is we're trying to make it easier to lift a heavy load here. And if you have this arrangement of these two pulleys, the rope goes round the pulleys like that, then it's a lot easier to lift this load up. You can have quite complicated arrangements, like in this diagram here. The more you have, the easier it would be to lift the load. We're only going to look at the very simple case where we have a fixed pulley like this, fixed to a ceiling, and then a string that goes over the top of the pulley, like that. And so what will happen is, the string, we pull the pulley on one side and the load lifts on the other side. In our case, what we're actually going to have is not a person pulling it, but we're going to have two blocks, one on each end of, one on the end of each string, or each end of the string. So essentially it's going to look like this. This is the simplest thing. We have the pulley, the string is in blue and that goes round the pulley, and what will happen is in this case I've got two blocks, each of one's of mass 2m and the other's of mass 3m kilograms each, and clearly what will happen is, because the 3m is going to be heavier than the 2m, the 3m mass will go down and the 2m mass will go up. So what actually happens is the string rotates the pulley. The pulley is fixed at an axle in the center, and the pulley itself rotates, and the string is stays on the pulley, stays with the pulley, and is kept there by friction. Now, actually, what we do is we model that a different way. We're going to have a fixed pulley. The pulley doesn't rotate. It's just a circle, and it is fixed. And the string is going to slide over the top of the pulley in our model, and it is going to be a smooth pulley, so that there will be no friction at the pulley, and that will mean that the tension is the same on both sides of the string, on both sides of the pulley. Okay, so if we go over here and look at this example, what we have here, it's example 13 in the book. It's a good example because it really does cover all of the sort of things that you get asked about pulleys. They come in more complicated arrangements than we have here, but everything that's in this question is the things that you get asked. Now, what is it? Let's have a look. Particles P and Q of masses 2m and 3m are attached to the ends of a light inextensible string. The string passes over a small, smooth, fixed pulley. So it doesn't rotate. It's fixed to the ceiling here. and it is smooth. The masses hang with the string taut, and the system is released from rest. So what will happen when it's released is, as I said, the 3M will descend, go down, and the 2M will go up. The 2M mass is P, and the 3M mass is Q. Now, the first thing to do is to mark on the forces which are acting on each particle. Now, what we have here is two particles connected by the string. But unlike when we had like two particles connected and like a car pulling a trailer, when both were moving in the same direction, we were able to consider this. Let's have the car as say 500 and the trailer as 200 kilograms. We were able to consider this as one particle of 700 and work out the acceleration from that. That's because both particles were moving with the same acceleration, because it was an inextensible string, and in the same direction. So the acceleration of the same magnitude and the same direction. Now this is not the same as in this case here with the pulley. Let's put that out, because even though the accelerations of both are going to be the same, have the same magnitude, they don't have the same direction. Q will go down, so that will accelerate down. Let's go that. So Q will accelerate down, but P will accelerate up. So P and Q, they both have the same magnitude, so I'm going to call that acceleration they both have A, but they are in different directions. We cannot consider this as one particle. Right, so let's consider the forces acting on each of the particles. Let's go for P first. The force acting on P will have its weight, and that will be 2 mg, and the tension in the string, which is pulling it up, and we'll call that T. There you go. On Q, well, we also have its weight. Oops. Just have to change that. Right. We always have its weight. Its weight is 3 mg, and the tension is holding it up there. Now put them in different colours so that it's clear that the red forces act on P and the green forces act on Q. They are, each particle has its own forces. We've also got the pulley, and we can put on the forces that are acting on the pulley. The string is pulling down. Again, I'm going to keep to that one. Right. The string is pulling down on that side, and it's also pulling down on that side. It's also being held up here as well by a force where it's attached to the ceiling. So some other force there, call that F. And so the purple forces are the forces acting on the pulley. So each component of this system has its own forces. Okay, so let's have a look at the questions now. Part A. Write down the equation of motion for P, write down the equation of motion for Q. The equation of motion is Newton's second law, F equals ma. So let's go for P. So I'm going to write it like this, and this is how you set out these questions. P. Oh dear, again change it to this. Right. P resolving, and now up or down. It's the forces are only vertical. Well, resolve in the direction of the acceleration, up. In this case, P goes up. So we just have T minus 2mg. T is up, 2mg is down, so that's negative. That's the forces. There are only two forces. F, so the total force is that, equals ma. 2m is the mass of P, a is the acceleration. So that's part one. Part two, you would have Q. Well, I'm going to resolve down for that one, because that is the direction of A. So we have minus T, because we're going down, plus 3mg equals ma, well 3m is the mass in this case, A. Not 3mg, that's the weight. 3m is the mass. Okay, so those are the two equations of motion. That's 1 and that's 2, part A. Part B, I'm going to go over here. Find the acceleration of each mass. Well, now we've got two equations, 1 and 2. 1 and 2. We want the acceleration, so we eliminate T. Well, I'm going to add 1 and 2. So the T minus T, that will disappear. 2mg plus, minus 2mg plus 3mg is mg equals 5ma. So dividing both sides by m and dividing both sides by 5, we get A equals g over 5. So A is a fifth of g. So they're accelerating. Q is accelerating down with a fifth of g, and P is accelerating up with a fifth of g. Part C, find the tension. Well, part tension, we will substitute in A. So I'm going to put here sub in one of them. So sub in one of these questions, and we'll get T. So we're subbing 1. We'll have T minus 2mg equals 2m times a fifth g, g over 5. So T will equal 2 2/5 mg, 2 2/5 mg, or 12 over 5 mg newtons. So that's A is in meters per second and then we've got D, find the force exerted on the pulley by the string. Well, on the pulley is the forces on the pulley are the purple forces. And the force exerted by the string on the pulley is just the T down and on both sides. So part C is going to be 2T. So that will be 24 over 5 g newtons. Okay. And therefore F will equal 2T, the same amount, 24 over 5 g, because the pulley itself isn't moving, and so the forces there must be equal. Total force must be equal to 0. Okay. Well, now I'm coming to part E and F. I'm going to stop this video now, and I'm going to do E and F on the next video, because I can only record 15 minutes in one video. Okay, so see you in the next video.